Hi everyone. In the previous session, we derived an equation for closed loop voltage gain of an inverting amplifier. And now in this session, we are going to derive equation for input resistance with feedback, output resistance with feedback, and bandwidth with feedback for the inverting amplifier with feedback. So first, let us consider the input resistance with feedback. This is the circuit diagram for inverting amplifier with feedback resistor millerized. While finding the input resistance with feedback, we are using millerization theorem for the feedback resistance. Input resistance with feedback is the resistance seen at this side, at the input side. From looking into the input side with the feedback present, we will get the input resistance with feedback. Whereas this Ri is the input resistance of the op-amp. So now what we have done is we have millerized the feedback resistance Rf, wherein this resistance Rf is split into two components. First one is this one, Rf by 1 plus A, and the second one is Rf into A by 1 plus A. So while at the input side, the millerized feedback resistance will be Rf by A, and after passing through the op-amp of gain A, the millerized feedback resistance at the output side will be Rf by 1 plus A into A. So this is all about the configuration of the inverting amplifier with millerized feedback resistor. Now look here. Since the input current to the op-amp is equal to 0, the same current that is flowing through R1 will flow through Rf by 1 plus A as well. So now these two resistances are in series, and this combination is in parallel with this input resistance of the op-amp Ri. So this input resistance with feedback will be equal to the series combination of R1 and Rf by 1 plus A, and this in parallel combination with the input resistance of the op-amp. So I'll write Rif as equal to R1 plus Rf by 1 plus A. This is series combination, and this is in parallel with this Ri, that is the input resistance of the op-amp. Now here, since Ri, by studying the characteristics of the op-amp, we have studied that the input resistance of the op-amp is very large, and we also know that the gain of the op-amp A, open loop gain of the op-amp A, is very large. So if this is large, this component will be very small, because the value of gain is very large and it is in the denominator, so the whole component will be very less, and whereas this Ri is very large, so the parallel combination of these two resistances, wherein one of them is very small and the other is very large, will yield a value 0. So this component is almost equal to 0. The remaining is R1. Now this input resistance with feedback is equal to R1. This is the ideal value of the input resistance, whereas this is the exact value of the input resistance with feedback. And next topic is output resistance with feedback, wherein we use Thevenin's theorem. There are three steps that we need to follow. First one is short circuiting of the input voltage source and inserting one more voltage source at the output terminal, and next step is to find the resulting current from this voltage source, and from this resulting current I'll find out the output resistance with feedback, which is nothing but the resistance seen at the output side. So the same steps what we followed for finding the output resistance with feedback for non-inverting amplifier, the same steps we are following here. So I need you people to write it on your own, but in the notes I have written it. I just want you to write. And the next topic is bandwidth with feedback. So while studying for the bandwidth with feedback in case of non-inverting amplifier, we considered a graph. If you remember, this is a graph that I considered, wherein at this extreme, the gain bandwidth product is 2 into 10 power 5 into 5, that is equal to 1 megahertz. Okay, and at this extreme, the gain bandwidth product is gain is 1 and the frequency is 1 mega, so 1 megahertz. So the gain bandwidth is 1 megahertz at this extreme as well. So the gain bandwidth product is constant from this extreme to this extreme. Okay, so this holds good if there is only one single break frequency, F naught. So this concept you should remember, and you all have conducted an experiment in analog circuits laboratory, wherein you have found that the gain for the amplifier with feedback is lesser than the gain of the amplifier without feedback. So the gain and the bandwidth is inversely proportional. So what I'll write now is bandwidth of the amplifier without feedback is lesser than the bandwidth of the amplifier with feedback. So now we know that bandwidth with feedback FF is equal to F naught into 1 plus AB. Name this as equation 1, wherein this F naught is the break frequency of the op amp. In the graph we considered F naught is equal to 5 kilohertz. Now this F naught can also be written as unity gain bandwidth by open loop voltage gain of the op amp. So F naught is equal to UGB by A. So this holds good for those op amps which has only single break frequency. Now I'll substitute for F naught in equation 1. So I'll get F is equal to UGB by A into 1 plus AP. Now go back to equation 5 and you will find that AF is equal to minus AK divided by 1 plus AB. So now this 1 plus AB by A will be equal to K divided by AF, wherein this K is the voltage attenuation factor. Okay, and so whenever you know the unity gain bandwidth of the inverting amplifier and you need to find out the bandwidth with feedback, you are going to use this formula. And if in case you know the break frequency of the op amp or the open loop gain of the op amp, you are going to use this equation 1 to find the bandwidth of the op amp amplifier with feedback. So for non-inverting amplifier, I got the bandwidth with feedback equal to UGB by AF, unity gain bandwidth by AF. So now bandwidth with feedback for inverting amplifier is K times the value of bandwidth for non-inverting amplifier. And one more conclusion that I will be drawing from this study is that if I consider AF as equal to 1, if I consider AF as equal to 1, this bandwidth with feedback for inverting amplifier will be UGB into K. And this bandwidth of the amplifier with feedback for non-inverting amplifier will be just UGB. So for a non-inverting amplifier, FF is equal to UGB, whereas for inverting amplifier, here I'll consider R1 is equal to RF. So this K will be equal to 1 by 2. So this bandwidth with feedback will be equal to UGB by 2. So UGB by 2. It is half of the value of the bandwidth with feedback for the non-inverting amplifier. So this is about the bandwidth with feedback for inverting amplifier. And now we have a few problems to solve, wherein for the inverting amplifier, R1 and RF value are given, gain is also given, input resistance and output resistance of the op-amp is given along with the break frequency. Now you are supposed to find the values of gain with feedback, input resistance and output resistance with feedback, and bandwidth with feedback. Now you know all the formulas. It is just a substitution of the values that is given, and first write whatever is given, the given data. Next write whatever you need to find. Next start solving the problem. So first you need to find the value of K and B by using the formula wherein K is the voltage attenuation factor and B is the feedback loop gain. And this 1 plus AB term will come in almost all the formulas. So just find and keep it aside so that simplification will become easier. And you'll find that the four values are so much. And this is the next problem. This is given as an assignment for you people to solve. Okay, I need you people to solve it, and all of you are supposed to submit the assignment before Saturday. Thank you all.